Okay, so I'm going to start recording. So today I want to explain two things. One, I want to show you some very clever techniques for lazy evaluation. So this is finishing what we started last time on advanced declarative algorithms. So last time we saw a bunch of Q data types. So I made a worst case amortized ephemeral constant time Q and worst case ephemeral constant time Q. So last time we saw ephemeral Qs, and I showed you how to make them very efficient. But today I want to show you persistent Qs. So a persistent data structure is very sophisticated because you can have multiple versions of it. And it's not so easy to do it. In fact, the code is very simple for these persistent Qs. It's very short code, but I want to explain how it works because it's kind of clever and not so easy to understand how it works, even though it's only a few lines of code. Okay, so first I want to start by presenting the ephemeral Q we saw last time and showing you why it's not persistent. Okay, and that's the first step, and then we will show how to make it persistent. Okay, how adding lazy evaluation can make it persistent. Lazy evaluation allows to do the reverse. Remember, we had to do a reverse sometime. So the problem is the reverse is then too late. With lazy, we can do the reverse much earlier, and that makes it persistent. But it's still only amortized, and we can also make it worst case constant time using another technique. The problem is that the reverse is monolithic. But we can combine the reverse with the append to make it incremental. Remember, for lazy functions, that our monolithic one means you have to evaluate the whole thing if you just want one piece. Okay, so that's not very nice, but we can make the reverse incremental. Okay, and this will be our most sophisticated algorithm. And it's only a few lines of code, but it's doing something really nice. Okay, so let me start. Let me first show you again the ephemeral Q. So remember, the Q is implemented as a tuple, front and the back, and when we insert in the back. But sometimes we have to move the back to the front, so we have this check function that will do a reverse and add this back to the front in some cases. Okay, so let me explain now the delete. So the delete now will take F and R, and it will take F, the X is the output, it will take it from the F. Now, the problem is that the F might be empty. But when we do an insert, if the F is empty, it's going to do reverse and move the R into the F. So let me show you how this runs. Let me do an example execution. So we start with nil nil. Okay. So the check function will do reverse if the F is nil. So let's say we do an insert of A. So this is going to give Q nil, A nil. Okay, it's going to add it here. But the check function is going to check that the F is nil, and it's going to do reverse. So it's actually going to do a check, and this is going to be A nil, nil. Okay, like this. Now if we do another insert, Okay. This is going to do A nil, and the result will be B nil. Okay. And this time the check will not do anything because this is not nil. Okay. Now let's say we insert a lot of elements to Z. We have QA nil. And here we have a huge number of elements. Huh? Okay, so it looks like this. So we have done a whole bunch of inserts. And now if we do a delete, it's going to take the A. Okay. If we do then another delete, it will take this one. So if we do a delete, it will take the A. But since the F1 then is going to be nil, the check will move this back to there again. So the delete, so we can do a delete now. Okay. So let's say this gives us, this is Q0, this is Q1, Q1, Q2, okay, let's say whatever, this is Q26 or something like that. So we have Q26. We have done all these inserts and we get to this. Now if we do a delete on this one, it's going to take the A off. But since the result is nil, it's going to do reverse. So it's going to do Q nil, Z, Y, B nil. Okay. And the X will be equal to A. But then it will do the check. Okay. And the check will do the reverse. So this will give us B, C, like this, and nil. Okay. So you see how it works, huh? And so this is amortized constant time, because the delete will only be done, the reverse will only be done once, and then you can remove all those elements. So this is ephemeral. Now what happens if we try to use it as persistent? So is it persistent? Well, persistent means you can have multiple versions. So here we have had Q0, we did inserts, Q1 up to Q26. Okay, and now we do delete. This gives us Q27. This is only one version, you see, yeah? Ephemeral, I only have one version. But if I want to do persistent, I will do another delete on Q26. And now I have two versions, you see? So if I do a second delete on 26, I will now have two versions, and I can make more versions. If I do another delete here, now I have three versions, all coming from Q26. So you see how it works with multiple versions, huh? Now each of these deletes is going to do a reverse. So let's say we do n deletes. No, let's say we do n inserts first. This is n inserts, and then n deletes from Q26, from the final version. This gives us 2n operations, right? 2n. The inserts are going to be constant time, but the problem is that each one of these deletes is going to do reverse. And the reverse will be order n, will be constant time n. So that means there will be n times n squared operations. Okay? See that? The n squared operations n squared, time, if you count the time, n squared, number of things you have to do, but I only have had 2nq operations. That means it's not amortized, it's not constant time anymore, because n squared divided by 2n is proportional to n, but for amortized constant it should be 1, huh? So this thing, it's not constant time anymore, you see, yeah? So it's correct, it's not wrong. The result is not wrong, it's just taking too long. It's not constant time. So if I use this queue in a persistent way, this implementation, I will have a order n amortized time and not order 1. Okay? So you see this one is not, it's not constant time anymore if I use it persistently. Okay? So, but we want to make it constant time. So how can we do that? We're working to do something quite clever. Well, I think it's clever. We're going to use laziness. So let me make a picture and give you some notion of what we're going to do here. So let me erase this. So the code is all in the Moodle, so you can look at the code. Let me make a picture and show you what's happening. Okay? And then we'll see how we can make it better. So in the ephemeral one, we had like this, Let me just make a picture. We have a queue, we do another insert, we do an insert, we keep doing inserts, and now we have a bunch of versions, like that. And this is a delete, this is a delete, this is a delete. This one is going to do reverse, this one is going to do reverse, this one is going to do reverse. So all of these deletes are going to do reverse. That's kind of a pain. Now, how do we make it persistent? Well, we want to do the reverse before. We want to try to make them, the idea is to try to make these reverses come earlier. Okay? So the idea is to move the reverse to make it earlier. So we want to do it here somewhere, this reverse. Okay? And if we do that, then it won't be having the problem here. Okay? So let me make to show kind of an example of how we're going to do it. Okay? So the problem is it still has to be amortized. Okay? So that means when we add them, when we do the reverse, we only do it when we can pay for it. So this is a typical way of doing amortized algorithms. So this is called the banker's method. So have you seen amortized algorithms in the previous course? Vous avez vu ça? No? In your algorithm course, you didn't see amortized algorithms? Yes, a little bit. The banker's method, the intuition is, the reverse is like expensive. It's taking money out of the bank. Okay? The reverse is taking money out of the bank, and you only take money out of the bank when the money is in the bank. So the banker's method, whenever you do a small operation, you put a constant amount of money in the bank. So after you do n operations, the bank has n pieces of money in there, and then you can do the expensive operation, okay? And it's amortized because it's spread over all the times you put the money in, okay? So the banker's method is for making an amortized algorithm, okay? So that's what we're going to do. We're going to, so let's say we do insert here. We have inserts. Okay? And each time we do an insert, okay, we put money in the bank. Okay? But we can only do the reverse when the money is in the bank. Okay? So let's do like that. So here, let me now make a different representation of the Q. So making it persistent. Okay, let me do a slightly different representation of the Q. Like this. Remember here we had F and R. The forward and the reverse list. Here we have F and R, but we also keep track of the lengths. The length of F and the length of R. Because keeping track of the length lets us count how many operations we did, so we can use the banker's method. Okay? So we have Q0 is going to be this one. So now we have Q0. Now let's insert. Okay. This gives us 0, nil, 1, A, nil. Okay. Like this. And now we can keep going. Huh? We can add more elements. At some point we need to do, we'll need to do a check. Eh? So we can keep adding elements. But now let's try to be smart so we can keep going. Huh? Let me go to the number here. Okay. So here we've added a lot of elements. We have this. But at some point we have to do this reverse. Huh? So how do we do the reverse? Well, we can do the reverse. So let's do the reverse while we're doing this. So we want to do the reverses early. We want to do them early. Now we're doing all these inserts, and if we don't do any reverses here, then we have the same problem. Okay, we want to do the reverses here. Okay, so we want to do the reverse early. Okay. Okay, so let's see how we can do that. Do 0, nil, 0, nil. So now let's insert A. Okay. We get 0, nil, 1, A bar nil. Okay. And now let's do a check. So let's do reverse now. Okay, so the idea for doing the reverse is that if the F is nil, then we do the reverse. So let's do reverse, like this. Okay, and here we have the computation, the reverse computation. And here we have 0, nil. Okay. Okay, that's good, right? So this one will be A nil, right? It'll be reversed here. But let's keep doing inserts now. Okay, let's do another insert on here. That gives me Q1. So this computation, I write it like this. 1B nil. Okay. Now the question is, do we want to do another reverse? See, the problem is we have to be smart in how we do the reverses here. Because we can do a long sequence. A long sequence of inserts. But somehow we have to already do some of the reverses. Okay? So we did here the first one. Fine. Okay. But we don't want to do them always. So the idea is, if we, let's say I do now another insert, so when you see what happens when I do another insert, this number will increase. Okay? So I want to decide when I do the reverses here. Now you see that each time I do an insert, this number will increase. Okay? Well, if I use the banker's method here, then the reverses are paid by the elements in the front. So when this number is about the same, approximately the same as this one, I can do reverse. Okay? Let me make I need to, some picture here. Sorry. So let's do it like this. So I have something like this. F, this is the length of F, sorry. The length of R. And I have two lists here. If I now do an insert, then I will add an element here. I will have LR plus 1. And if I do another insert, I have LR plus 2. Okay? And if I do a check with reverse, then this one goes back to 0. Okay? Okay, like this. Now I do a check. This one goes back to 0. But now this one will be LF plus LR plus 2, because it all moves to here. Okay, and here we have lists that are growing. So you see that eventually when I do this reverse, I move all these elements to here, so this length goes bigger, but this one goes back to 0. But if I do another insert here, okay, then again, this will be the same number as before. LF prime, this one will go 1. And again it will increase. 1, 2. Okay? So the idea is that I'm counting here. These are increasing. Okay? But I can remove them up there when I can pay for it. Okay? So this reverse will take time here. So the idea is that I will only do the reverse when the LF is paying for it. So this LF, so when this LR becomes about the same as LF, then I can do the reverse. So the idea is the following. I have F and R, okay? So when I do inserts, that R is increasing, so it starts from 0, it's increasing, and when it gets to the point of LF, then I can do the reverse. Okay? Then I can move it in. And then it goes back to 0, and then I do again. So I'm basically moving from R into F whenever the R is big enough. Okay? So that's basically the idea. Okay? And in order to in order to do the computation only when I need the result, so I don't need to do this reverses until I do the deletes. Okay? I don't want to really do the work here, or else this is going to be expensive. So I'm going to make them lazy. So let me show you the code for this. Let me see. Let me first give you a scenario. So here's the scenario. Here's the execution scenario. Okay, so I start with 0, 0, 0, 0. And now I do an insert of A. Then I get 0, 0, 1, A, 0. Okay. And now we're going to say we're going to do the reverse first. We're going to do a first reverse here to put something there. This will be 1. And here I will actually have a reverse function call here. This one goes back to 0, 0. Okay? So this is what happens when I do a first reverse, a first insert. Now if I do a second insert, okay, then I get 1, 1, 3, 0. Okay. And now I do a third one. 1, 2, C, B, 0. Okay, you see this one is growing now, and as soon as it gets bigger, a little bit bigger than this, then I will do a reverse again. So this gives me 3, so 1 plus 2. And here is now another computation. So this computation goes in here, but I have another computation adding this one there, and I go back to 0, 0. So basically, it's growing piece by piece. It starts when I have the first one, and then it goes 3, and then it will basically almost double each time. Okay? So let me show you the code for this. So here is the code. So the Q is created, 0, 0, 0, 0. When I do an insert, so I take the Q, length of F, F, length of R, and I add 1 at the end here, X bar R, and I increment the R by 1. And when I do a delete, I will take an element off of F, F equal X bar F1, and I will do length of F minus 1, and the R is not changed. So here I have the check function. Okay? So the check function basically compares the two lengths. So you see how it works. The length of F and R, whenever I do an insert, the length of R is increasing. And when I do a reverse, the R will be moved to F, and then the F will increase and the R goes back to 0. So basically it goes like this. The R goes to F, F goes up, and then when I keep doing inserts, the R goes up again, and when it gets to the level of the F, it goes back, so it's like this, So the F's will only increase when I do this check function, okay? So you see that I'm comparing the length of F and R. So the R starts by being 0, and each time I do insert, it goes higher. And as soon as the R gets, so it actually has to be, to make it work, it has to be 1 higher, it has to be just about the same as F. So when the R gets to the level of F, here, then I move the R to the F. So how do I do that? So I will append F and the reverse of R. So basically, the F here is not nil, The F is not nil. So I don't actually want to do an append here, because it's going to take time, So if I actually do the append here, it's going to append F plus the reverse of R. But the F is not nil, because the F, I'm still only doing inserts. It's all growing. So I will do a lazy append of F together with a lazy reverse of R. So I combine F plus the reverse of R. But I'm not actually doing it yet, because I'm not actually doing it yet here, because I don't actually want to run the L append of F yet, okay? Because each time I do, it will give me extra overhead, okay? So I'm not going to do it yet, but I make a lazy call here, F plus the reverse of R. Okay? And then the R goes back to 0. And then if I keep doing inserts, the R is increased again. And when the R goes back up to the level of F, then it reverses. It does again. It combines it again. The R is moved again to F. And I create another lazy function call. Okay? So I'm creating, so while I'm doing inserts, I'm creating all these lazy suspensions that are moving the R into the F. Okay? But I'm not doing it yet because there's no reason to do it until I actually do the delete. Okay? There's no reason to actually to move it in there yet. So I create lazy suspensions. So then when I do a delete, I need F, okay? And this will trigger a part of this execution here, okay? This will trigger the lazy append and the reverse. But it will only trigger a part of this, because lazy append is incremental. Okay? But when it does a reverse, it does the whole thing, because reverse is monolithic. So if the F is different from nil, it will do this, and it will take off an element X. Okay? So it will do part of this to get the first element. And then it makes length of F minus 1, and it has F1, which is one less element. So if I keep doing deletes, it's going to keep doing part of this computation. So how does this work now when I have multiple versions? So I'm telling you this is persistent now. So when I have multiple versions, the delete will only be done once. And the reason is that I'm doing I'm creating the lazy suspension before I split into multiple versions. So let me make a picture of this, just to give you an idea. So here I have Q0, I'm doing insert Q1 up to Q26, and now let's say I split to 27. So now I have multiple versions. So here I do delete, delete. But the lazy suspension is created here. Okay? And when I need the value, this delete will cause this lazy suspension to be activated. Okay? But the lazy suspension actually binds the result. So once this is executed, this calculates the F, the new F. This second delete also needs the values. But because it's a lazy suspension, it's already evaluated in the first delete. That means the second one does not have to evaluate it again. It's already been evaluated. And the result F is shared between the two versions. So that means the reverse is only done once here, and not twice. Okay? Remember in the old version, the reverse was done each time I create a delete. Each time here, it makes it n squared and all. But here, because I have lazy suspension in advance, the reverse is only done once. And the result of this lazy suspension binds the variable here, and the second delete will see already the result. Okay? Doesn't need to evaluate it again. It only evaluates once. So that means that the lazy suspension, because it's created in advance, this variable f is actually shared between the two versions, and so it's only computed once. Okay? So that means that this is actually it's persistent, amortized constant time persistent. Whereas the other one was not constant time, because you had to do the delete everywhere. Okay? So you see, doing these lazy suspensions early on will make it persistent. So the trick really to make it work is to do them at the right time. So that's why we have this condition here. We only want to do them when we are allowed to. We don't want to make things more expensive by doing them everywhere. If we did them everywhere here, then we would have to do many, many, many appends, and we would not gain anything. So we have to do them rarely, infrequently here. So in fact, we're only doing them once. Here we do it once, and then R goes back to 0. And when the R goes back up to F, then we do it again. So this condition here makes it that we don't do these lazy suspensions very frequently, very rarely, because otherwise we would not gain anything, okay? So with this code, then we get a amortized, persistent, constant time. So the persistence comes from the laziness where the suspension is created in advance and is only calculated once. Okay? When I do delete, one of the deletes, and it's constant time because I only have a small number of these. You see, I have this condition here, so I'm not creating this every single time. That would be too expensive. So basically the F is doubling each time. Huh? So I have F and R, I move R into F, and then R goes back to 0, and the F is twice as big. And then the R goes up again, and then I move R into F, so the F is basically doubling each time. So these are actually done very infrequently, okay? It's only done whenever I double the size of the cube, okay? So you can see this very simple code here is doing something quite smart, okay? So in order to understand this, I really encourage you to run this code and to look at this, to look at these values while you're running it, okay? Do inserts and see what happens. Run the code, okay? So this now is giving us an amortized, persistent, constant, so amortized constant time, persistent cube, okay? Using the laziness. And then there's just one more thing I want to say, is how I make it worst case constant time. So this guy is still amortized, unfortunately, because we have this reverse in there. So reverse is a pain. Huh? Remember I showed you last time that reverse is monolithic. If I reverse n element list, it takes order n. That means these lazy suspension, when there's a reverse in there, I'm going to do a lot of work, okay? So if I delete one element and I have to do reverse, it's going to reverse a huge list. So that's why it's not worst case constant time. That's why it's amortized. Huh? Because some of these deletes will be, this one, the one that does the reverse will be order n, which is a pain, okay? But we can actually make it also worst case constant time. And that, I just want to show you the technique we use for that. So let me show you one final technique. Okay, so I'll have to let you write it on the board. So we have now, let me first summarize what we did, and then I'll show one more final technique, and then we're done with the advanced algorithms. Then you really know the full power of laziness. So we have now an ephemeral, so this is all amortized, that we have a persistent cube, and both of these are amortized. Now let me try to make it worst case constant time. So let me explain now what's going on here. I want to make now the step from amortized persistent to worst case persistent. So remember, we made the step from ephemeral to persistent, but both of them are amortized. Now I want to make this the step from amortized to worst case, and it will still be persistent. So going from amortized to worst case. Persistent. Okay, the problem is this thing. The problem is the L append in the check. So there's a lazy, so this is basically a lazy reverse, huh? So I have a lazy append, and this is actually, it's a lazy reverse, huh? So I take the reverse and I put it inside the lazy function, but it's still monolithic, huh? So this is lazy append. The problem that this one is monolithic. That means when I do the reverse, when I activate this suspension, when I need the elements here, I'm going to do the whole reverse. That's a pain, okay? So how can we get rid of this? So we want to get rid of this monolithic reverse. So this is the call that we want to keep, but somehow we want to change this so that there's no more monolithic reverse. Okay? But how can we do that? Well, we are saved, in a sense, because there's a lazy append here. We're doing lazy append of F with reverse of R. Okay? And F and R are going to have almost the same length. When I do this reverse, the length of F and the length of R will be almost the same. Okay? So the idea is to combine append and reverse. So the idea is to make another function that does both of these. Okay? So I will create a new function. Let me call it Apprev, append reverse, okay? And it has both F and R as arguments, okay? And it also has the accumulating parameter of the reverse. So I will take this append of F, so that's the F here, and the reverse of R, and this is the accumulating parameter, and I will make one function that combines those two. And the idea is that while I'm doing the append, each time I do a little bit of the append, I will also do a little bit of the reverse. Okay? So that makes the reverse incremental. So let me show you the code in more detail to show you how that's working. So here, let me show you first an append, and then I'll show you how they're combined. So I have an append, let me say f of b, so I pick the names of the variables, f of x, f2, then x append f2b, and nil, then B. So this is append, okay? It's appending F and B. Now let's make a reverse definition. So reverse R B, so B is the accumulator. Case R of YR2, then reverse R2 YB, okay? So this is this reverse definition. So this is a standard append. You can see I'm appending F and B. Case F of X bar of 2X bar append F2B. This is just append. And this is the inner loop of the reverse. So the way the reverse works is that I take an element off of R and I move it into B. I do a recursive call Y bar B, and when the R becomes nil, the result is B. So the B is accumulating the result. Now I combine these two. So let me call this one Apprev, LRB. And now, FRB. So I'm looking both at the F and the R here. The F and the R. So the idea is I'm going to do these two steps at the same time. Here I'm taking one element out of F. Here I'm taking one element out of R. And I do a recursive call in both cases. So I'm going to do both of these at the same time. So I'm going to take both of these. So let me make a tuple. Pair FR, okay, of pair XF2, YR2. So you see, all I'm doing is combining these two. The F goes into XF2, like here, and the R goes into YR2, like here. So, in a sense, I'm merging the reverse into the append. I'm adding some extra stuff here. Okay? And then I do the result. So I'm still doing an append. So I still create the result. X bar, Apprev. Okay? And here I have F2. But also R2. And then Y bar B. Okay? So you see, here I'm doing the append part. This is the append part. But I'm also doing the reverse part here. I'm taking an element off of R and putting it in front of B, just like here. Taking an element off of R, putting it in front of B. I'm also taking an element in front of F and putting it in the result. Okay? So you see I'm combining. So this is a function that does both append and reverse. Okay? And how does it end? Well, at some point F is going to go to nil. The F will be empty. But what is the value of R? Well, we have actually length of F. Remember, we have this condition. We have this condition in the check that the R and the F are almost the same length. In fact, the R will be exactly one higher than the F. Because when the R starts from 0, it grows, and when it's just a little bit higher than F, we do the check. Okay? So that means when the F gets to nil, the R will have one element left. Okay, which I call Y here. And then the result is YB. Okay? So here, what is this function actually doing now? It's actually appending f with the reverse of r. So when I call Apprev of of f r nil, it's actually computing, it's doing the append of f with the reverse of r, right? That's what it's computing actually. Because while it's recursing down the f, it's putting the x's in front, so it's recursing down the f. And when the f goes to nil, it returns y bar b. So y bar b is actually the reverse. So while it's recursing down the f, it's building the reverse. The r goes to y bar r2, and it builds the reverse. Exactly like in this function. So when the f is exhausted, it returns the reverse. That means while it's doing the append of f, it's building the reverse. Okay? Now why are we doing it like that? So why do we have this little bit complicated function here? Well, because this complicated function is incremental. Okay? So instead of doing L append and then lazy reverse, we do L Apprev like this, okay? And here we put nil, it starts with nil. So if we replace this lazy call by this one, and we make this lazy, then this function is incremental. So you see the trick? We have moved the reverse into the append. So while we are doing the append, we're also doing the reverse. That means there is no more order n operation. Every single step of this append is constant time. Okay? Because while we're doing append, we're doing also the reverse. And this gives us the final code, the final one. So let me show it to you. So the code is almost the same as before, except now we use Apprev instead of append of reverse. Okay. So this is a function that does both append and reverse. It appends f with the reverse of r. You see that? And when you call it, you start by calling it with b is the accumulator. So you start with nil. So this will do append of f with the reverse of r. This is our Apprev function. And once we have that, the final Q is this. This is our most sophisticated Q. Okay, so this is the final Q that we have. So again, we have insert and delete. So you see, the insert is kind of simple. It's putting the x here, increasing the r by 1, and then calling check. And the delete is removing an element from f and doing lnf minus 1 f1. So the insert is increasing r and the delete is reducing f. Okay? And then we have this check call. And if len f less than len r, so what this basically means is that the r is growing when it gets higher than f. So if f plus 1 is equal to r, then I do the reverse, the moving of the r to the f. And here I call L Apprev, the function I just defined, the lazy function. So this lazy function is completely incremental. That means none of these operations will ever take order n. And also, when I do a delete, when I do several deletes in different versions, only one of them will compute this. The others will use the result because they have access to the same variable. So this code is a persistent worst case constant time Q. Okay? So it's not so, the code is not so complicated in number of lines, huh? But to really understand how it works, you see, it's a little bit subtle, huh? I think you agree with me that it's a little bit subtle, huh? But you can see the power of laziness here, huh? So, the power of laziness. So here we really have a worst case, constant time, persistent queue. This is actually a very sophisticated algorithm, huh? If you want to implement this kind of algorithm in Java or non-declarative, it's very hard, because they will always be ephemeral, huh? Whereas here we have a persistent thing. So if you need a system that has multiple versions, this is a very powerful technique, huh? Okay? So that's all that I'm going to say about these advanced algorithms. There's actually more stuff. So I only am talking about a small piece of this book, huh? So this whole book is giving you clever stuff. But this gives you a good flavor of the power of laziness. So what I want you to remember from this, many years, is that lazy evaluation is actually extremely powerful, and it can make very efficient algorithms, even worst case persistent versions. Okay? Okay, so let me make now a break here. After the break, we go completely different. So now we're going to finish the part of the course on declarative programming. And so now we are week 5. In fact, let me first make an announcement for the midterm. So the midterm will be all the material up to today. So up until the end of declarative programming. So week 5. So that will be the material for the midterm. I would prefer to do the midterm during week 7, which is the SMART week, yeah? Semaine SMART. So I want you to tell me what is the good time for the midterm. So I want you to tell me, you have to organize yourself and tell me what you think is a good time, because I know you have other courses with deadlines and other midterms and things. So it's up to you to arrange it so that you don't have so many conflicts, okay? So you should tell me what you think is the best time for the midterm. So the midterm will be 1 hour, and I remind you it's can give you up to 5 points for your final grade, but there's no penalty. If you do very bad on the midterm, if you don't do it, you have no penalty, because you will see the same material on the final exam, and I take the maximum, huh? So if you do well on the midterm though, you have already got points for the final grade, okay? So that's something that I just want to announce, so please tell me when you would like to do the midterm, okay? So I'm expecting you to figure it out and tell me what are the best possible times. So I would prefer doing it in the Semaine SMART, the SMART week, which is the 7th week, which is in 2 weeks. Now we're the 5th week. And because that's what it's made for. There's no courses during this week. So midterms and things normally would go that in there. So someday in the SMART week, tell me what are the possibilities. So you should organize yourself to make sure if somebody has a constraint and they have another midterm, for example, on Tuesday, then probably we don't want to do this one also on Tuesday, okay? So you want to spread out a little bit, okay? So I wait for you to tell me that. So I'm very flexible, so you can do the midterm, so we can arrange it, but I'm expecting you to tell me what are the good times for you during the Semaine SMART, okay? So the material is up to including today. So the material from next week is part of the course, but it's not part of the midterm. Okay? So today I want to finish by, now we leave declarative programming. So up until now, I have shown you only declarative paradigms, equivalent to functional programming, and I've shown you that they're actually quite powerful. You can do concurrency, you can do higher order, you can do very efficient algorithms, persistent, ephemeral, and so on. But you can't do everything. There's limits, actually. So that's too bad, because declarative is actually the best way, because it has a lot of advantages, but you can't do everything. So I want to look carefully why you cannot do everything, and how we go beyond it. Okay? So I'm going to start by first saying, what is it, declarative execution? It's actually an execution of a lambda calculus program, okay? You didn't see it in this notation, right? You don't see it so much, but on the foundation, all declarative programming is lambda calculus, pure lambda, okay? And we will see that this has actually a limitation. We'll see that a lambda execution cannot interact with the real world while it's executing. That's kind of a very weird thing, so I'm going to explain it to you. So in order to interact with the real world while it's executing, we need to extend. And then we leave declarative. Then it's not declarative. That's why we need mutable variables, or communication channels, or even a hardware clock is part of the real world. Huh? So we're going to make some extensions, and the two most important ones are mutable variables, which you use very often, like in Java, which are called cells here, and communication channels, which are called ports in this course. So you can say this is Java and this is airline, okay, if you want to connect it to two languages. So Java goes this way and airline goes this way. Those are two ways that you can go to go outside of declarative, okay? Okay, so up until now, we have seen declarative. Up until now, I have been force-feeding you declarative and telling you how great it is, etc. So we've seen sequential functional, we've seen concurrency, deterministic data flow, concurrent programs, we've seen lazy evaluation, and I show you that it's all very efficient. There's no efficiency problem. You can actually make very efficient algorithms using the declarative techniques. So that's all very good. And ideally, so my view, after many years of writing lots of big software and trying to make it work and so on, so I've been writing lots of software, the point is your program should be completely declarative. That's the ideal, okay? Because it makes lots of things simpler, and you will see that later on. Debugging, so correctness, testing, maintenance, so upgrading, it's all a lot simpler if your program is declarative. And you will see that. And in fact, the industry is moving in that direction. All the cloud analytic tools, for example, are actually quite declarative. They're very large, distributed, fault-tolerant systems running in the cloud, doing very powerful computations. Well, they are declarative, because that's the only way to really make them work if they're on such a big scale, okay? Otherwise it would be too complicated. So the industry is actually moving in this direction. But the point is, now, you can't really do everything. There's actually limits to declarative. You cannot write your whole program like that. And it's not because of any problem with declarative programming. It's because there's a fundamental thing there. So I'm going to show you why not, okay? So we need to add stuff that's non-declarative to make it really work in the real world. But luckily, we don't really need so much. We need just a little bit of non-declarative, so most of your program can still be declarative. So you still want to try to make most of it. So why can't you do everything? Okay, it's actually very simple. Declarative execution is equivalent to a reduction of a lambda expression. Okay, so I'm not going to show you again lambda. Okay, if you've seen the previous course 1104, you know what it is. Lambda is this very simple calculus that actually lets you do all kinds of computation. Okay, you start with an initial expression, which is like a functional program, and you reduce it in reduction steps and you get final result. That's it, okay? And this is Turing complete, so you can do any kind of computation here, which you will understand if you have seen the previous course, okay? All kinds of things, numbers, lists, logical operations, lists, you can do everything, recursive functions, everything in this calculus, okay? So you've seen that. I'm not going to repeat that, so we assume that, okay? But then we have something else. We have this calculus actually has some power. And the power comes from this Church-Rosser theorem. It has a property called confluence. This is the real power of declarativeness. That means no matter how you reduce in any order, so sometimes you have a choice, you can choose different reduction orders, you will always get the same result. So there's nothing like race condition or non-determinism. No. You will always get the same result. The final result, En, is independent of the reduction order. Now that's very powerful. This is really the reason why lambda is such good. I mean, there's two reasons. One is that it's Turing complete, and two is that it's confluent. So this is the real power, and this is an amazing property. So we are blessed with this great property here, okay? But this power is also the weakness. The power we get here will also be the weakness. So how is that possible? Okay? Well, it's very simple. You start with E0 and you go to En. So all the information is already in there. This is your whole program, okay? E0. So while it's executing, no information can go in there. This thing cannot interact with the real world while it's executing. It cannot, for example, if you're typing on a keyboard and you want to put in some information while it's executing, you cannot do that. Because, well, yeah, you can do, but it's not declarative anymore if you do that. Because in the lambda, everything is already in the initial expression. All information is in the initial expression. You're not allowed to add anything later. So this is what you have to give up. So if you want power, you have to give up something. That's very normal, kind of. So if you want this confluence power, you have to say that nothing can be added later. This is the sacrifice you have to make in order to get confluence. So that's very nice, and in many cases, it's okay. If I have a big computation, it's fine. But what if I do want to add something later? Well, then I'm not declarative anymore. Okay? So you see, it's actually very simple, But many people don't understand this, and it took me many years to understand this. Seems crazy, In the 20 or 30 years ago, I did not understand this simple thing. So how is that possible? And in fact, most people even today will not understand this simple thing. Because it's too simple. People love to understand complicated things, but there's been long discussion on what is functional programming and so on, but people really don't understand the limitation. So I'm presenting something very simple here, so you don't need to look very far here. There's no hidden weirdness here. It's very simple, actually. So let's say I want to interact with the real world. Let's say I have a program that's running, like a text editor, and I'm typing in text while it's running. Well, a running program is a sequence of reductions. So this is a running program. Okay? Each of these steps, each reduction step, takes time, of course. This is implemented on a computer. This is using transistors and logic gates and whatever, and it's clocked, and it's very complicated. But the point is, it takes time. Okay? So this whole thing is going to take some time. That's very reasonable, That's logical. Because the execution happens on a computer, which is a physical artifact in the real world. So this is taking time. And this execution can be very long. And if it's a text editor that's running, it can run for days. An operating system can run for weeks. If it's not buggy. If it's buggy, it crashes and you have to reboot. But actually, good operating systems can run for weeks or months without stopping. So this thing can go on for a long, long, long time. But it interacts with, it doesn't just sit there and do a computation. It interacts with me, okay? So if I type something, I'm putting in information here. S0 is going in. Or if it's displaying something on the screen, information is coming out during the execution. Well, this S0 and S1 is not lambda anymore. Because lambda does not allow that, okay? Lambda is only that. So if I want confluence, I'm not allowed to do this or that. The input S0 affects E2. It's some input coming in. And the output, E4, S1, is an output which is not the final result. So this is a weird output that has nothing to do with lambda, and this is an input that is changing the computation. So both this and that are not lambda anymore. So that's the very simple thing. So once you allow this kind of thing, you don't have lambda, so you don't have the power. You've given up the power. Okay? So this is something you see a lot in things like anime and stuff. So I'm a big fan of anime, and usually when you have a very powerful character, they have to give up something to get that power. It's very intuitive. Actually, it's the same here. So if you want the power, you have to give up this interaction. If you want confluence, which is really where the power comes from, you have to give it up. Okay? So I like to give you kind of colorful explanation, but it's very similar to these overpowered characters, They are giving up something. Usually they are giving up something to get the power. Okay? So, summarizing, the good and the bad. Okay? Lambda calculus is confluent, but there's no real-world interaction. Lambda calculus is the confluent reduction of an initial expression to a final result. So this has very strong mathematical properties, and it's basically the Church-Rosser theorem. But this lets you reason about programs easily. Debugging is eased. Testing is much, much easier when you want to test multiple components. Then each one can be tested separately, and the complexity is additive. Whereas if it's not declarative, it's multiplicative, so it's much harder. So testing is easier here, optimization is easier, maintenance is easier. Also, for parallel and distributed execution, like cloud tools, MapReduce, Apache, Flink, whatever, these cloud tools, it's much easier. And there's no efficiency penalty. You can see you can do very efficient algorithms here. Okay? So this is all very good. But there is a weakness. You cannot interact with the real world. So during execution, we would like to accept inputs coming from the real world and outputs going back. I'm typing text into my text editor, and I want to see the displayed text. That's not declarative, okay? The execution is a step-by-step reduction of an initial expression to a final result. Reduction steps take time, and inputs will arrive during this time. The reduction cannot use them unless you could put them in the initial expression. So you can say, yeah, it's like the initial expression is different, but you cannot do that because you do not know the inputs in advance. You only know them during the execution. So you cannot put them. You might say we do a trick. Okay, all those inputs, it's as if they were in the initial expression and we're done. But you can't really do that trick because you don't know them in advance. Because if you would know them in the beginning, it's like looking into the future. You don't know them in advance. So you can't do that, okay? So that's the thing. Okay, so what do we do now? We want to interact with the real world. So we have to leave declarative programming. It's terrible. We have to go away and do something else which is not declarative. To interact with the real world, we need to add something to these declarative paradigms. We need a way to get input and output during the execution, which is not declarative. Usually this is called imperative programming. So imperative as opposed to declarative. So when people talk about imperative programming on one side and declarative on the other side, this is what they mean by imperative. So this lets us interact with the real world, good, but we have to give up the goodness, the power of declarative programming. So then the question is, well, I don't like to give up all this power. I want the interaction, and I want to keep my power, of course. Can we have the declarative properties and interaction? In fact, we cannot. Okay? Nobody has figured it out, and I don't think it's possible. We cannot. So we have to give up the power if we want to interact. Okay, but it's not that bad, okay? You don't have to give up the power all the time. You can in fact keep it most of the time. So most of the program can actually be written declaratively. In real-world programs you can see that. Most of the code can be actually purely declarative. And you only need small pieces where it's actually doing the interaction, okay? And usually there's very few places, small number. So I'll give you examples of this. You can see many examples of this. So usually most of the code will still be declarative, which is good. Most of it will be declarative. Okay. So, I can say a few things about legacy code, existing systems. So usually they're not really designed like this, because people didn't really get it. Okay. Usually they do too much imperative. They are too much written as if they could interact with the real world anytime, and that you're giving up the power all over the place. So old programs in Java are typical bad examples, okay? So if you want to improve, if someone is giving you legacy code and you have to maintain it, the way to do that is to try to make it more declarative. If you want to make your life easy, make it more declarative. But of course there's huge amounts of legacy code and you're going to be stuck with that, okay? So I cannot help you with that. I can only help you with how to make it better after. Okay, so how do we interact with the real world? How does a program interact? So there's many ways. So fundamentally, it's not just like displaying on the screen. We're looking at it now in a fundamental way, from the viewpoint of the lambda reduction. What does it mean to interact? So here I give you 3 ways, but there's many ways because it's all information going into the reduction or leaving. There's many ways you can do that. So here's 3 typical ways that this works. One way, one of the simplest, is a hardware clock. I have a clock that's counting nanoseconds. Quartz, crystal, whatever, nice clock, okay? And whenever I read the clock, it tells me the time. That's not declarative, okay? The reduction, the time of the reduction has no significance for Church-Rosser. The time that I read when I do a reduction doesn't mean anything. And maybe when I do it again, I will read a different time. So this is non-declarative. This is information coming into the reduction. Okay? But even things so simple, like a mutable variable, a variable that you can update more than once, that's non-declarative. It's like you write to the variable. I call it a register here, but it's any variable. You write, and later on you read. So the writing is leaving the reduction, and the reading is information coming from outside. And it all depends on the order. If I write twice to the same register, the latest one is going to be the value. If they're concurrent, for example, then maybe it changes during one reduction to the other. So I'm giving up Church-Rosser when I do this. So a mutable variable is already something non-declarative. And there's another way, which is also very common, which is a communication channel. So the difference between a variable and a channel is that in a variable, you only see the last value. So if I write twice to a variable, you only see the last one. Whereas a channel, you will see all of them. Okay, if I send two things to the channel, I can read both of them. So the channel does not lose any information. So that's another way of doing it. So there's basically, these two ways are both reasonable, and many systems will do one or the other. Okay? So the mutable variable is the Java style, I'll call it. The communication channel is like Erlang style. Okay? But both of them are non-declarative. Okay? So with all of these, the executions will give different results depending on the exact timing and order of the reductions. So this is not Church-Rosser. This is not confluent. This is proving that these are not declarative. Okay? So they're not declarative. Okay. So let me go and get be more precise. So here's the hardware clock. So here's my reduction, my declarative reduction. But some of these are actually reading. So this, from E0 to E1, I'm actually reading the hardware clock, T0. So E1 will know this value. It reads time T0. And from E2 to E3, I'm reading again the clock. And from E4 to E5, I'm reading the clock. And I get these different numbers coming in to the reduction. And the exact times that I read will depend on the timing of this. So it depends on the implementation and how the clock speed and everything. So totally non-confluent. Totally non-lambda. Okay? For a lambda reduction, it doesn't matter how long it takes. It doesn't matter what the order is. The result is always the same. But here the results will change if you change the clock speed, or if I heat up the quartz crystal, it will run at a slightly different speed. So there's lots of effects. So it's not lambda. Okay? So reading hardware clocks is already non-lambda. But we can do more things. So here's the mutable variable case. So this is a slightly different kind of interaction. So I'm writing into a register, or I'm reading. So assume I have one register. Okay? You can have many variables. In this case, there's only one register, like one variable, and you can write and read. So the read will return the value of the most recent write, of course. If you write twice, the second one overwrites. So here, E0 to E1 will actually write X into the register. E2 to E3 will write Y into the register. And E4, E5 is doing the read, so you will actually read Y. And you read Y and not X, because the Y is after the X, so it's overwriting the X. That's how variables work. It's very simple, So here again, the result of the reads depends on the order. Okay? If I switch the order of these two, then I'm going to read X. But Church-Rosser would not care about that. If I switch the two order, the result should be the same. But it won't be the same, because I will read X instead of Y. You see? So for a lambda reduction, the result will be independent of the order. But here it's not. It's not independent of the order, so it's not lambda anymore. Okay? So that's an example of an interaction. Your regular old Java variables are already that. Okay? Here's another one, slightly different. but it resembles it. This is the communication channel example. So let's say we do a FIFO channel, first in, first out. That means the information will come out in the same order it goes in. So here again we have our reduction. We send X on the channel, so E0, E1 will send X on the channel. E2, E3 will send Y. E4, E5 will receive from the channel, but it will receive X, because X was sent first. Okay? This is FIFO. The first things that are sent are the first that are coming out. It's like a pipe, huh? Things are going through. So E4, E5 will receive X, and E5, E6 will receive Y. The order of the values depends on the order. If we flip these, then it will be YX, okay? So the order of the received values, again, it depends on the reduction order. So it's not confluent. And this could be concurrent, and so it's not confluent again. So communication channel is another way of being non-declarative, okay? So you see, here we have three different ways, and this is I'm showing it in a very fundamental way here, in terms of lambda with something added. So in the real world languages, like Java, that's all hidden. You don't see all the lambda underneath, but it's all like this. So all programming languages will do something like this. So all languages that deal with variables, they will behave like this. And if you write a variable from two different threads, then the one that's last will be the one you read. Okay? That's all languages are like that. Okay? So this is extremely general. It's true for all languages. Okay, let me now show you an example. Let me now show you an example of an application that is mostly declarative. This is the same example as we saw in 1104, if you remember that course. But now maybe you can understand it a little bit better. We're building client-server, Amazon, okay? So the server is Amazon making huge amounts of money. Jeff Bezos, very rich guy, trying to go into space because you're paying him whenever you buy something. But we're not talking about that. We're talking about the code here. So the client code is running on your browser. And there's another client, and there's millions of clients. So everything here can be declarative except for one thing. It's where the server receives the requests from the clients. Okay? So this application has a liveness requirement. Okay? The server must accept each incoming client request in a reasonable time that depends only on the travel time from the client to the server. So when client 1 sends a request, the server has to accept it in a reasonable time that depends only on the travel time, and it does not depend on client 2. Okay? For example, if client 2 sends a request, it should not affect client 1. Now, notice, the order of the requests cannot be determined in advance because it depends on the precise timing of the clients. So the server does not know in what order the client requests are coming in. Could be any order. And even if the two clients, if client 1 is doing his order before client 2, maybe this is a very slow connection, and this is a very fast one. So even then, client 2 maybe comes first. Okay? So this is an example of a communication channel. So this is exactly an example where it's using this channel here, right? So there is actually a channel here from the clients to the servers. The clients are sending into the channel, and the server is receiving from the channel. Okay? So, but there's only one channel here. Maybe the server has millions of lines of code, and it does if it's Amazon. There's a huge database. There's all kinds of stuff here. Even your browsers are a complicated piece of software here. And there's all the networking software and everything. All of that can be declarative. There's only one piece that's non-declarative here. It's the point where the server receives from the clients. So this is an example where you can see that most of the program will still be declarative, and we only need a small piece of non-declarative. So this is very usual, okay? Most systems will be like that. Most systems only have a small part that has to be non-declarative. So you can still, everything I taught you on declarative programming, you can still use it, okay? You don't have to throw it away, because most of your code will be declarative, hopefully, if you write it good, huh? So this is an example. So it's the same example. I like this example because it's very simple and still very realistic, okay? Okay. So it turns out the two most important non-declarative operations that people invented. So over the years, people invent many weird kinds of operations. But after all that, the two most important ones that are considered today are the mutable variables and the communication channels. Okay? So we're going to show both of them in this course. And many systems are using these, both. Huh? So the mutable variables, we are going to give them precise meaning. We are going to call them cells, because you can update multiple times, so it's like a box, so we'll call it out a cell. And languages like Java are using this approach. This leads you to things like locks, monitors. Systems with transactions are doing that. So this is a very common approach. The other one is the communication channel, which I showed you. So in this course, we're going to call those ports. Information comes in through the channel. This leads to message passing. So this is also a popular approach. So a lot of internet networking is doing that, of course. But there's also programming languages like Erlang, which is used based on this approach. So this is something called multi-agent programming. So a lot of telecommunication systems are built on this, but you can use it for general applications. So these are like the two common approaches, okay? So in the rest of the course, we're going to focus on these two, and I'm going to show you really nice advanced techniques in both of these. Okay, these are the two important non-declarative ones. So I'm going to explain a little bit cells. So this is partly a review. So some of this in the beginning, it'll be similar to what we saw in the previous course. So a cell is just a box. You can call it a register. The box has a content inside. It also has a name. The box has the name, and that's called the address, or the identity. So that's something that's very common in programming languages. You can have the name of the variable, but in the implementation, there's actually going to be a physical part of memory, which has an address. So the processor actually is going to know the address of the variable. Okay. In our model, the content is going to be a variable, a single assignment variable, but you can change the content. You can replace the content by another variable. Okay. So there's three operations. You can create a cell. So here we have to create it explicitly, yeah? So if you don't create cells, your program is by default declarative. So that's really good. So all the programs you write, they are totally declarative unless you create cells or ports. And you can do an assignment. So this uses colon equal notation. This is a pretty standard notation. And then you can read the content. So this uses this at symbol, the access notation. So if you want to read it, you do like that. So that's how cells work, and it's very intuitive, and you know them already. So here's a cell with the content 0. I can change the content to 5. If I do y is equal to x, then actually I have a second reference to the same cell. So this is called aliasing, and this is something that you see in languages with pointers. You can have two variables pointing to the same content, for example. And if I do y gets the value 10, then of course x will see the change. Huh? So that's all stuff you know. Huh? So this is kind of a common thing. Huh? And if I have two cells with the same content, x and y, they both have the same content, but if I compare x and y, it's not the same cell. They have different cells. So you have to distinguish the cell, the identity of the cell, and the content, which is not the same thing. Okay? So this is something that most languages have. It can be, it's called references or pointers, pointer dereferencing, whatever. So languages will all, most imperative languages that use mutable variables will do something like this. If you do content of x comparing with content of y, this one will be true because the content is the same, okay? And I give you some semantics here. So I want to be very precise. So far we have a single assignment store with variables that are single assignment. So we add a second store to this, sigma 2, which I call the cell store, which contains pairs. So the full non-declarative store is actually, sigma is actually the union of these two. So, and then you can actually give the semantics. So a new cell is actually creating a pair. So in the next slide I give a picture. And a cell will have a name. So I use Greek letters for that because I'm not using them for anything else. These are constant, unforgeable constants. So C is the name of the cell, C here, and X will be the content, okay? So C and X are both in sigma 1, but the pair is in sigma 2, of course. And then I have an operation called exchange. So exchange is actually doing an assignment and a read together. So in fact, you only need one operation. Huh? You don't need to do both assignment and read. The exchange will do both. So X, so here I have a cell C. X gets bound to the old value. So the cell is C colon Z, so that's the old value. And the new value will be Y, so the new pair will be 1. So this thing will read the old value and update in one operation. Okay? So I like to make it as a picture. So here's a picture. So here we have sigma 1 and sigma 2. So sigma 2 has the cell. So I now do an exchange. So X will be bound to Z, which is the old value. And the cell gets a new value, which is Y. Okay? And there's an argument. There's about too many arguments there, sorry about that. I have to update that. I don't know why, I was brainwave. So C, X, Y, so the Z is not part of that, huh? So I will fix that. So the read and the update are atomic, which means the scheduler will never stop in the middle. It does both of them in one indivisible operation. That's important when you do concurrency. Okay, so that's it for cells. And the next thing is ports. Ports, which are actually very simple things. So this is the communication channel. Huh? You can actually see them as named streams. So remember in the language we have stream, which is a list with an unbound end. And there's two operations, new port and send. It's the same like for the cell. Huh? You have new cell and exchange. Here you have new port and send. So you create a port with the stream S, and you add X to the end of the stream. So with this, we can actually solve the client-server program. Huh? With 1 million clients, each client will send its message to the port, and the server will read the stream S. So this allows you to solve the client-server. Oh, you need one port. Okay? So here we can do some examples. If I create a port, if I send A, I get A bar underscore. If I send B, I get AB underscore. If I do the two sends in the different threads, then the result is non-deterministic. It all depends on the scheduler. So what are the possible results of those two sends? You tell me, you know what it is, right? You know, you should know. Because the scheduler depends on how it schedules those two. So the semantics is very easy. So again, we have a single assignment store, sigma 1, and now we have a port store. Let me call it sigma 3, which also contains pairs. Remember the sigma 2 is the cell store. So when I create a port, I will create a pair. So a port is also a pair, like a cell. And when I do a send, I will actually bind S to X bar S prime. So basically I'm extending the stream, okay? This is a list pair, concella. So if you make a picture of this, it looks like this. So here is port, S is the end of the stream. I do a send, and I get S prime, and S is bound to X bar S prime. So I've extended the stream, and the port also always points to the end. And again, the send operation is atomic, etc. So this is the port. So those are the two things, cells and ports. Okay? The full store has a single assignment part and a multiple assignment part. So you can consider sigma 2 and sigma 3 together, actually, because they're both containing pairs. Okay? I call this the multiple assignment store. And they can have both cells and ports. Okay? So if you look at the client server now, I can give you the code. So here's the code. It's so simple. So I create a port. Each client will do a send, M to the port. And the server is just a loop that reads the stream. It takes off the message M. It handles the message. So it does your Amazon order, whatever, and then it does a recursive call. So the server is reading all the messages on the stream, and each client is sending messages. This will solve completely the client server example. So you only need one port for that. So now we're done for today. So declarative paradigms are best. They cannot always be used. So they have power, confluence, but the power comes with a sacrifice. They cannot interact with the real world. So in order to do the interaction, you have to add imperative concepts. So the two common ones are cells and ports. So basically Java and Erlang. And the lesson is you should use declarative as much as possible and add imperative only when you really need it. And usually there's only a few cases. But current languages are way too imperative. They're too much imperative, So both Erlang and Java are way too imperative, in fact. Why is that? Because they were both invented in the 1980s. And in the 1980s, people didn't understand this, okay? So they're both very old. In fact, they're about the same age. They're both invented in the late 1980s. Java is a very old language, and it's got a lot of old weirdness in there, But there's better languages coming, but Java is still a big thing. And Erlang also, it's a very old language. I mean, they're nice in some ways, but they're much too imperative. And that's a fault that comes because they're old. It doesn't mean it's the right way to do it. It's not because the languages that you use are doing it that it's the right way. It's only for historical reasons. So now we know better. But between knowing better and changing languages in industry, it's 30 years, okay? So 30 years from now, when you guys are close to retirement, this will be all over, this issue. And I will be in the retirement home in those days. I will be sitting there watching the TV or something. But it's the difference between research and industry, it's always 20 or 30 years. So I know that this is the way to do it. But that's not what the industry is not going to change immediately, Of course not. There's so much invested. Millions of programmers, they know these systems. There's so much code written in them. And so it's not changing. Even if they know how to do it better, you can't re-educate millions of programmers. They won't do it. They won't go. The only way is to create a new generation of programmers that knows how to do things better, and that's you guys, huh? All the way. All right? That's the way it goes. So that's the real world. It's hard to, things are hard to change, even if you know what the right thing is. But still you have to go in that direction. So I'm telling you the things in the way I think are the best. Okay? So I'm very old, 61 years old, and I have lots of experience with programming. So many, many years, and I have made lots of stupid mistakes when I was young and so on. So I try to tell you how to avoid all that. So I'm trying to tell you the right way. So it's up to you to accept what I'm saying or not. You guys are free agents, but I try to give you the good arguments. Okay? So Java and Erlang are very old, but better things are coming. And actually it's the cloud systems that are the advanced guard. Because the cloud tools have to run on hundreds of machines. Okay? They have to run when there's failure. And the only way really to make that work is to make them declarative, because it's much too complicated if it's not declarative, okay? So by force, the cloud is pulling the rest of the industry toward declarative systems. So if you take the cloud computing course, which I recommend, you will use these cloud tools and you'll see that they're very declarative. Much more than Java or Erlang. Okay. Okay, so let me stop here. So these slides are on the Moodle. So starting today, we will have slides, right? So there will be slides from now on. So that's all.